So, if you think back to Physics 220, you're like, Physics 220, or whatever equivalent class you had, the first physics class with calculus, okay? Things probably started out with like motion. You dealt with things that were moving around, and then you talked about forces and determined like, hey, forces are making these things move. And once you got done with that, you might have started talking about energy, things like potential energy and kinetic energy, conservation of energy, and it was almost like a new way to do the exact same things. In fact, you probably discovered that like with things like projectiles, you were like, oh, I can use all these motion equations, or I can just say, hey, it has this much potential energy and this much kinetic energy, and I can quickly get to the answer a lot easier. And maybe some of you thought like, this is a lot better. Why did they teach me all that other stuff and make me do it that way? Okay? We're doing a similar thing now. We talked about forces. We talked about the electric field. Those two things are sort of tied up together as like one way to describe how some forces, some charges impact other charges. It was a way to describe that like positive charges will repel each other. Negative charges will repel each other. A positive and a negative will attract each other. And that's essentially what we spent the last two chapters analyzing in a very intensively mathematical way that kind of hurt a little bit. Agreed? And now you're going to have to do a lot of homework and practice a lot and go back and try to sort all that out and ask each other questions, ask me a lot of questions, send me a lot of emails. I just hit, I have a button, it just replies LOL and archives it. Like, I want to develop that just to mess with everybody, like lol and archive. I think that'd be fantastic. I could get in a lot of trouble that way, I think, especially if it's like department chair, lol and archive. Someone else, lol and archive, but no, I'm not going to do that. Ask questions as you delve into those two chapters. We're going to start thinking about a lot of the exact same things from the standpoint of energy. So you can see right at the top there, electric potential energy, okay? So here's the thing you need to remember. First of all, this electric force, you might remember the idea of conservative forces. Conservative forces, like, they don't waste energy. In other words, when they do their work, they don't just throw energy away. So we have things like gravity, that's like gravity can have a potential energy. So like the pencil right now has gravitational potential energy. If I drop it, well, it loses its gravitational potential energy. But I can just pick it right back up again and get that energy back. It's not like it's just like gone forever and I can't get it back. On the other hand, something like friction, right? It's like, well, if I shove the iPad that way, it stopped because of friction doing work and essentially taking away the energy that I gave it. I gave it some energy. Friction said, I don't care about your energy. I'm going to stop this thing, suck all the energy out of it, and throw it away, and you can't have it again. Friction is non-conservative. It doesn't keep the energy around. If it were conservative, like gravity is, you might be like, push the thing this way, and then friction says, yeah, you can have it back. And that'd be a creepy world to live in, right? It doesn't work that way. How come it doesn't bother you when gravity does it? Gravity threw it back to me. Why doesn't that bother us, right? I threw it up in the air. I gave it some energy. Gravity said, I'm going to stop it. I'm going to stop it. I'm going to take away its energy. And then, oh, here, you can have the energy back. I'm going to push it back to you. It's a conservative force. It didn't waste any of the energy. Friction doesn't work that way. Boy, I wish I had a string right now attached to this so I could just be like, whoop, and pull it back. Friction just takes the energy and says, it's done. I did not conserve it. On the other hand, the electric force is a conservative force. It doesn't waste energy. If it does some work and takes energy away from something, it stores it as potential energy and can put it back into the charge. So conservative forces have potential energy associated with them, okay? So I have this force that is the electric force, and it's going to be connected to electric potential energy. And maybe you used U for potential energy, maybe you used PE, whatever, it's all kind of the same. The electric force is associated with the electric potential energy. So if I were looking at the change, let's see, do I want to do it that way? I don't know. Do I? Yeah, let's do that. The change in potential energy, meaning the difference in potential energy, say, between two different points. It's equal to the negative of the work. This is like an equation you should have seen last semester. This is just in general for any potential energy. And we can use that equation and get some new stuff dealing with the electric force and the electric potential energy relatively quickly. Does anybody remember anything about work and what equation we have for it? It's basically a force times a distance. There's more complicated forms of that, but essentially it's force times distance. So in this particular case, I'm going to write it as an electric force, since that's the one that we're worried about, times some distance over which that force acts. So if I want to know how much work is being done by an electric force, well, the force is being applied to a charge, and that's happening as the charge moves a certain distance. Notice it's also equal to how much the potential energy of that charge changes as it goes from one point to another. And I can rewrite this one more time because we have an equation for the electric force. We can connect it back to the electric field. It's equal to QE. So we have that equation for both work and change in electric potential energy. So this is equal to work and the change in potential energy. So what do we mean by electric potential energy? In a way, it's not all that different from gravity. Okay? If I take a mass and put it in some gravity, right? Right now, it has gravitational potential energy because it's feeling the force of gravity and it could fall. Okay? If it starts at this point and gets pulled by the gravitational force downward, you might imagine as it's going lower and lower, well, that force is doing positive work on the mass and the amount of potential energy is decreasing until we get to the floor and there's no potential energy left because it can't fall any further. Okay? We have a similar sort of thing in an electric field. So again, this electric field concept, think of it like gravity. Like gravity is in existence in this region of space, and if I put a mass in gravity, it gets moved by the gravity. The electric field exists in this region of space, and if I put a positive charge in that electric field, it feels a force and gets moved. All right? So you can almost think of this region here, and I hate that this is so close together. In fact, let's draw it again ourselves. Let's imagine that there is an electric field that points like this, and it's being created because there are a bunch of positive charges up here, and there are a bunch of negative charges down here, creating this electric field in between that region of space. So that if I take a positive charge and put it all the way at the top, it can't go any higher in the electric field. It's going to have the most potential energy it can have. So here it has high electric potential energy. And of course, it's going to feel a force that repels it from those positive charges, and it pushes it in the same direction as the electric field. It's almost like it's falling to relate it back to gravity again. But just keep in mind, I only oriented it like this to make it kind of like gravity, so that down was the direction it wants to go. I could tilt this at an angle, and then my charge would sort of fall along the electric field this way. I could make it go all the way upside down, and now my charge would fall up in the direction of the electric field. So in a way, like, gravity is a thing that exists. We know how it works. We don't have a lot of control over it. If I have something that's charged and an electric field is something I can control, I can sort of make things move whatever direction I want them to. So it's like this powerful, fake sort of gravity, right? That I can make charges move the direction I want. So that means by the time the charge gets all the way down here, well, now it doesn't really have any potential energy left. We could say it has low electric potential energy. So as the positive charge follows the electric field, its amount of potential energy is dropping. Just like when the mass follows the gravity, right, and goes with the gravity, its amount of potential energy is dropping. Do you see the comparison between those two? Maybe a little bit, okay? Here, a positive charge falls in the direction of the electric field, has lots of potential energy when it's near other positive charges, and low potential energy when it sort of gets to the end of the line, when it's near the negative charges. Keep in mind, mass is just mass, right? Mass, there we go. Mass like attracts other mass. When I'm dealing with charges, I have positive and negative charges, which means I could do something like this. I could put a negative charge in here. If I put a negative charge here at the bottom, what can you say about its potential energy when it's at this location? It has high potential energy, right? Because it really wants to go this way. It can fall in this direction against the electric field. So we would say here a negative charge has high potential energy, electric potential energy. And once it gets done falling and reaches the other side where there's nowhere else left to go, then we would say it has low electric potential energy. So this whole thing is analogous to gravity, but in a lot of different ways. It's like more powerful, it's more versatile. We can do a whole lot more with it, and we have a lot more control over it with the technology that we have. Maybe one of these days we'll have, you know, artificial gravity where we can control it and just be like, you know, I think all of us are feeling a little heavy today. We just like turn the knob down and we start to float out of our seats. That'd be kind of fun. Kind of scary, kind of fun. Maybe one of these days in the Star Trek universe that I'd very much like to live within. Sigh. One of these centuries, one of these centuries. First, I need to live for a long time. So we need to reach the singularity, and then I need to plug my consciousness into a computer. And yeah, I don't know, things have turned sideways now. So it is 4:23. I'm not going to introduce a new topic. Instead, I'm going to draw a couple of pictures on a new slide for you. Hold on, I'm just thinking here. There's a lot of whiteboard space up here. As many of you as want to. Like, it would be easier for me to see your work and be like, what are you doing there? And like kind of point out what's going on and for you to ask questions. If you want to bring a group of 3 or 4 people and crowd around a little area of the whiteboard and work these problems, I think it's good for you and good for me and good for your awakeness, sort of in general, if you're not just sitting there being like, I don't know how to do this problem. I don't know how to do this problem. Instead, you're like up here kind of fighting with it with someone else, okay? So either find a spot on the whiteboard or mill about and find a group of 3 or 4 people and try these problems, okay? I'm gonna put one up here. All right, how is everybody doing on this Physics Friday? It is Physics Friday, right? Physics Friday, Thursday? Something kind of like that, yeah. Yeah, where is everybody today? What happened? Strange. Just like a week ago, people were clamoring at the door trying to find a spot. Huh. It's curious. Yeah? It's disappointing. Now I'm sad. I don't know if I can do this now. Look at all these people missing over there, like a whole slew. Yeah. We should, shouldn't we?
It'd be very nice for us.
Yeah.
And for the
We should have like extra class because they're not here, like to punish them. Or does that punish you all? I'm not sure which. And me? Yeah.
Because you have to be there too.
Yeah, it punishes all of us. We can't do that. Ah, I like that. I should teach things today that all of us agree to never share with them. And then it is a question on the first exam.
Yes.
That's pretty good. Yeah.
Give us like some credit.
Like the answer for 30% of the test is B. The last third of the test is B. And now you know that. No. That'd be pretty fantastic, though. Boy, that'd make grading easy on that part of the exam. I couldn't complain too much about that. You know, I'd like to,
Well, you really don't have to.
but I really don't have
The
to.
answer could just be B for like math questions.
Oh, yeah. It's like,
B for math questions. Oh. So they think it's like the answer is like 60, but it's B. Okay. Huh. Things to think about. We should see who shows up on Tuesday and following. Now maybe those of you who are here, you're thinking like, dang it, I was thinking about skipping out. And now you're wondering what might happen. Ah, somebody just got revealed. I saw that. Slapping someone across the aisle. That's wrong. All right, so let's see. Today, I have tried 2 experiments today trying to record the lecture another way and failed both times. Mostly because I ran out of storage on my iPhone both times in 2 other classes, which was depressing. I wanted to record 4K video because I was like, ooh, it'll look fantastic on YouTube, right? And it was like, that's going to be 15 gigabytes, and I didn't have that much room. So I was like, fine, we'll try 1080p. And it's like, still ran out of space. So I'm stuck with the system here, which is 720p, which, you know, it looked okay, but it could look better. You know, you kind of want to be able to see everything that's up there in ultra high definition, but I don't know. We'll have to see. So I'm going to do this for now, and we'll go from there. I'll experiment some more. I'm not guaranteeing, once again, that I'm going to record this every time. People who aren't here, you might not ever get this lecture. Maybe they were thinking, I'll watch it later. Maybe you will, maybe you won't. We'll see. Maybe I'll just leave gaps in the middle. I'll just hit pause every now and then and just kind of stop. So we were talking about electric potential energy. Electric potential energy. Keep in mind all 3 of those words together mean something different than just electric potential. Notice on the next slide, like the word energy drops off. Don't think that like we're just going to start using shorthand. It's like, forget energy. We know it's energy. These are actually 2 different things. And I hate the fact that 2 very different things have almost the same exact terminology. It's a bit of a problem. So let's go back and first describe again what electric potential energy is, and then I'm going to contrast that with the next slide and what electric potential is. So we've got some equations up here that will tell us how much potential energy a given charge has, and it's all dependent on where that charge is located inside an electric field. Keep in mind, if I take a charge and just put it somewhere where there's not an electric field, it has no potential energy because it has no motivation to move somewhere else. Much like if I take a piece of matter and just put it in deep space somewhere where there's no gravity, well, it has no gravitational potential energy because there's no force that's pulling on it in any given direction, okay? It can't fall. In this particular case, if we put the charge in an electric field, it sort of wants to fall in the direction of the electric field. It feels a force that way. Keep in mind, if I use a negative charge instead, it will feel a force the opposite direction. It sort of wants to fall against the electric field. We say that when there is the possibility for that charge to move, to feel a force and go somewhere else, it has electric potential energy. Much like a mass, if it wants to feel gravity and go somewhere else, has gravitational potential energy. Okay? Do you have the idea of what this potential energy means? Do you have questions? Do you get it? Yes? Yes. Okay? Let me point out something on this diagram over here at the right. I feel like if we keep zooming in far enough, we're going to like see a little creature hiding in here somewhere, you know. Like, Hi. But, there's nothing there. Just forget that, okay? Notice these words, potential energy, are pointing to the charge itself. In both cases, and this is important, like they took this line, they drew it literally into the charge, and that was no accident. Because it is the charge that has potential energy. It has a certain amount of energy because it exists in this electric field, okay? When we talked about masses and gravitational potential energy, it is the piece of mass that has gravitational potential energy because it will fall somewhere, all right? This is different from, next slide, potential. Leaving the word energy off. Let me start by looking at this diagram over here. Notice the arrow here is connected to these words, and it's kind of just pointing to this point right there next to the charge. Again, when they drew these diagrams, this was no accident. The energy is something that the charge possesses. The potential is something about a point in space where there isn't necessarily a charge at all. It's saying that this location right there next to that solid plate has low potential. On the other hand, over here, this little location right here up against this plate is a location that has high potential, all right? If we go back and look at the definition, I literally wrote out, it's like the potential, quotes, of a point in space, how much possibility that location possesses, okay? Let me explain a little bit more by, well, again, relating it back to gravity. So if we were dealing with gravity, notice they put two different size rocks up at the top. We could assume that those probably have different mass. Well, if they are a certain position off ground, we would say that those two pieces of mass both have gravitational potential energy, but a different amount because they have different amounts of mass. You might remember that gravitational potential energy, we could write that as, if you don't mind, can I just write it as PE? Sometimes U is used, but PE, gravitational, is equal to M times G times H, right? So how much gravitational potential energy a piece of mass has is not just based on where it's located above the ground, but also based on how much mass it has, okay? On the other hand, if I were to just say, remove these rocks, yeah, that didn't really remove them, that just colored them, right? And it's like, yeah, you have green rocks now, fantastic. Pretend they're just not even there. How can we do this? I don't know what's happening at this point. They're not there anymore, okay? Those locations where the masses were, they're still in existence there. There's still points in space there that exist this height above the ground. We might say that these locations have potential. They have possibilities. They have options. Because if I put a mass in those locations, those masses will now possess potential energy. It's a subtle difference. Do you hear the way I'm describing those two things? The locations where nothing is located, these locations at height h above the ground, have potential. Literally, they have gravitational potential because if I put a piece of mass there, it will possess potential energy, okay? So in terms of the equations, what we might do is write something like this. Boy, I really hate this, but V is what we use for potential. And this is part of the reason why I switched from using U here, because writing a U and a V, trouble, right? So potential energy is mgh. We might say that the potential of those points in space is just G times H. If we were to get rid of the mass, like don't put a piece of mass there, and let's just talk about how much opportunity those points have. Well, they have some potential because there is a height above ground level, and it exists inside of a gravitational acceleration or a gravitational field, all right? So let's relate this back over to electricity. And and electricity and magnetism and all this sort of stuff. And let me make sure I write down the right things. Question?
So V equals GH, no rocks are gone.
If the rocks are gone, those points at that height still have potential. Okay, so we might call this gravitational potential. And this up here is gravitational potential energy. Okay, now over in the electricity side of things, right? Notice we again have this little setup where we can create an electric field in between all these positives and negatives that are on these plates. So there's an electric field that's pointing that way because a positive charge would be pushed from the positive side over toward the negative side. And notice this time they don't have masses. They've decided to put two different charges here, right? One is just charge Q and one is charge 2Q. Kind of like the masses where I had a mass and then a bigger mass. Now we're dealing with charges. We put them in here, and when they are in this location, we've already learned that they have potential energy, electric potential energy. And we had an equation over on this previous slide, QED, okay? So potential energy, electrical, and I'm gonna write this as a magnitude, is equal to Q times E times D. Okay? If I take the charges out, that hasn't changed that region of space. There's still an electric field here, and that point in space is still a point that has a lot of opportunity, a lot of possibility, a lot of potential. Because I know that if I put a charge there, it will possess potential energy because it wants to be pushed this direction. So notice the way these equations are working out. Here I said, okay, remove the mass, and then I can say that this location above the ground inside of gravity has potential. Look at this equation. I can say that if I take out the charge, so let's do that down here, V sub E just equals E times D. These look an awful lot alike, right? Notice there's a certain location, okay? It's a certain distance away from the farthest place it can move to, and it's inside an electric field. Here I had a gravitational field. Here I have an electric field. Those points in space have potential. So the difference is points. Where nothing is has potential. Charges at those points have potential energy. Okay? Can I say that again? Points in space have potential. Charges placed at those particular points will possess potential energy. Okay? So we could go over to this diagram on the left. Not the left, that's the right. Yeah, I've got problems. Apparently it's very much Friday, Thursday. Ugh. We can look at this diagram and like completely get rid of these charges. And we can analyze this setup and say that over on the left-hand side of this region, we could say over on this area, in this region of space, there is high potential, okay? And that amount of potential is going to be less and less and less and less and less as I go across here until I get over on the other side, and we would say that regions of space over here have low potential, okay? The amount of energy a charge has depends on whether I put it into a higher potential area or a lower potential area, okay? Just like, well, the iPad can fall to the floor, right? This region has higher potential than regions right next to the floor. If I put the iPad here, it's going to have higher potential energy. And if I put it in a region of lower potential, it'll have lower potential energy, okay? This is a way, kind of like we did with electric field and force. We went from force, talking about like this charge exerts a force on another charge, and then we sort of like abstracted away from that a little bit and just said that there is an electric field here such that if I put a charge there, it'll feel a force. We're doing almost the exact same thing here, saying this region of space has some properties, it has potential. If I put a charge there, it's going to have energy. Okay, these things are all analogous, they all sort of fit together, but they are hard to grasp the first time through. Mostly because this is a lot of stuff that we can't see and touch and play with, and it's just conceptual, okay? I'm hoping in your labs, when you get to play with some of this stuff, that some of it kind of hits home a little bit more, okay? So electric potential energy. Let me see, I have some equations here to give you. Okay, so this one, first of all, the electric potential is equal to the potential energy divided by the charge. And if you think about it, that's essentially what I did when I moved from here down to there. I divided the charge out, and that gave me the potential. We could also write this as U divided by Q if you'd prefer to use that terminology instead. Also, the unit for potential is the volt. The unit for the potential is the volt. And it turns out that it is equal to 1 joule per coulomb. 1 joule per coulomb. And also, beautifully, this is the part you should like. It is a scalar. Yeah, at least one person understands the significance of that being a scalar. Scalar, yay! You don't have to deal with vector addition when you're having multiple things to deal with. So this is supposed to be the easier way to do similar problems. When I'm dealing with energy and potential, it's a scalar. I can just add and subtract things without having to worry about any direction information. So let's switch over to the next slide. A few points I should make. First of all, typically when we're doing problems with potential, we want to focus on a difference in potential between two different points. A difference in potential between two different points. So I could write that something like this. Delta V, a difference in potential, is equal to the potential at point B minus the potential at point A. Or if you wanted to use that equation we had just a moment ago, we could say that this is the potential energy at point B minus the potential energy of point A divided by whatever charge is at those locations. So you see some of these equations starting to fit together now. So since typically we're dealing with a potential difference, if we want to know, like, I don't care how much the difference is between here and here, I want to know the potential at this point, just one of them. The only way for me to get this is to know the potential at one of those 2 points. And there is a way that we commonly do this. We pick a reference point, and this reference point is known as ground, which is perhaps something you've heard of before. When we're dealing with something known as ground, this is a location where the potential, the electrical potential, is equal to 0. So that means if I know the difference in potential, say, between this point and ground is 0, well then the amount of potential at this point is equal to the potential difference. You can see that in this equation, okay? And by the way, ground, we're gonna do circuits and stuff later on. Typically this thing, ground, is literally the ground, meaning Earth. It turns out that the Earth is basically a sort of an infinite reservoir of electrons, of charge, and I can send it a few more charges or I can take a few out of it, and it sort of doesn't care so much. It's negligible to something the size of the Earth. It allows us to have a region of space where there really is no potential, okay? Sometimes also, or we'll say alternatively, we will use R equals infinity, meaning far, far away from any other charges. as a location where V is equal to 0. And I think that sort of makes sense because it's just like with the mass. If I put the mass way out in space somewhere, it doesn't feel any gravity, so it has no potential energy from gravity standpoint. The same idea works with charges as well. And then one more equation. You can see here at the bottom it says the potential difference tells us something about how much energy a charge can gain or lose, or how much work it can do. And we can get back to this idea just by simply rearranging some of our equations. The change in potential energy is equal to Q times the potential difference, or Q times VB minus VA. So reading through this equation, if I have a charge Q, and then there are 2 points where I know the potential. So maybe I know the potential here, and I know the potential here, okay? If I take the charge and it moves from one point to the other, and I know the value of the charge and what the difference is in potential between those 2 points, this will tell me how much its potential energy increases or decreases as it moves between those 2 points, okay? So what are we going to do with all of this? First of all, a slide just with clarification. Notice over on the right, U is electric potential energy, and it is a type of energy which means its unit is joules, just like energies you had before. Other types of potential energy, kinetic energy, all that type of stuff, units of joules. Different from that is this thing that we're calling electric potential. For it, we use V, which is also its unit is in volts. Sometimes we get even a little more lazy with that and just say potential all by itself. So if you hear just the term potential, we're talking about the exact same thing. We're still talking about V, and it's measured in volts. So these two things at the bottom are exactly the same, but they are different than potential energy, okay? So we've got potential, and we've got potential energy, two different concepts. Just in case you care a little bit, potential differences that exist kind of throughout the world in different things to give you a feeling for what a volt is and kind of where those things are experienced. A flashlight battery is built such that there is a difference of potential between one end of the battery and the other end of the battery, which is typically maybe about 1.5 volts, give or take a little bit more. You can see as you move up from that, an outlet in your house is typically about 110 volts of potential difference. And keep in mind, potential difference combined with charge starts telling you about how much energy is there, how much potential energy. And of course, as these go up, these are seemingly more energetic, right? Until we get all the way up to the top, thundercloud to ground, which results in lightning. Lightning happens because there's charge that's moving from a very high potential to a very low potential, and you can see the difference in potential there is 10 to the 8th volts, which results in quite the current flow or charge flow from clouds to ground, which is kind of sad, scary, and exciting, and scary. But a little exciting to watch, but scary, okay? So let me ask you a few different questions here related to potential and potential energy. I'll give you a moment to read it, and then we will talk. Hey, things aren't blowing in the breeze today. Should I do this? Did you kind of enjoy that today? The other day, is it kind of soothing? You're like, please stop, I'm trying to read. Okay, I'll stop. I wonder where this phone goes. Can I call anything on this phone? Is that like a phone? Or is it like the scary emergency phone that only like dials one number if I pick it up? You should call yourself. See if it works. You might just pick it up and they're like, police. You know, I don't know. Why is there a phone? I don't need a phone. Do you need a phone in here? I don't think so. What's the answer? Any thoughts? 1, 2, 3, 4, or 5. Vote. Vote if you think you know the answer. You're like, we haven't even been reading. We're thinking about this stupid phone. Who says 1? Who says 2? Who says 3? Who says 4? Who says 2? I caught some of you. Who says 5? They feel the same magnitude force, but opposite direction. I would agree with that. Number 3 is meant to trick you just a little bit. But keep in mind, force is equal to, well, Q times E. A proton and an electron have the same Q, and they're in the same E. So they're going to feel the exact same force, but they're going to want to go opposite directions in the electric field. So let's quickly draw that in. The proton is going to be pushed this way, and the electron is going to be pushed that way. So in a way, that's a little bit of a review question from last chapter. What about this one? One, 2, 3, 4, 5, 6, 7. We ran out of questions. I don't know what else. So they experience the same force, but keep in mind an electron and a proton have very different masses, right? A proton is much heavier, which means that the lighter thing is going to have more acceleration. So that would be the electron in this case. Will experience more acceleration. Let's see. So we need to connect this back to the last chapter somehow. The last chapter was all about electric fields. It turns out that these things are not separate or distinct. They're sort of like different ways of looking at the exact same problem. Just like there were problems in Physics 220 that you could analyze with forces, and you could maybe look at the exact same problem in terms of potential and kinetic energy, okay? 2 ways of looking at the same thing, but there are connections between them. So any given problem, if there's an electric field that's there are going to be places that have high potential and places that have low potential inside of that electric field. So we have graphed this here real quickly. This is the exact same situation we had before, right? Positive here, negative here, an electric field going this way. We know that on this side we have high potential, because again, it's defined on what a positive charge would do, and then the potential goes down as we approach the other side, and you can imagine eventually the charge is going to sit against this. Regions of space there have no potential because the charge would have no potential energy remaining. If we were to graph that, and this is meant to line up directly with what you see above, okay? I don't think it does because it's pretty close. I don't know that I copied it perfectly. So this corresponds to this side, and over here we're looking at that plate, okay? We start with some value of potential, and it's as high as it's ever going to be over on this side, and the amount of electric potential I have linearly decreases until I get to 0 over at the other side, okay? In this particular case, we're dealing with a constant electric field, and we can see how the potential varies as we move to different points in the electric field. It's a linear decrease. If I were to write this as an equation, it turns out that the electric field corresponds to the negative slope of the potential, or the negative change in potential with respect to, let's write this as L. This is basically a distance or a displacement. Now let's write it as distance, since that's what they did at the bottom there. Notice, potential versus distance. There's a slope, a rate of change. That's what this equation is giving us. The negative says it's a negative slope, okay? This tells us how the potential changes in an electric field. Question?
Does the observation that whenever we're trying to observe this kind of scenario where you're using a proton carry over to this as well?
Yeah. All of these equations are set up based on the proton. Everything gets flipped exactly reverse if an electron's in play. Okay? It's all based on what a proton would do. So I can take this equation, and again, keep in mind, it's the negative slope of the potential. The electric field is the negative slope of the potential. And we can rearrange this into an integral. And we're going to do that on the next slide. I'm going to go straight over here. And all I'm going to do is rearrange this and solve for the potential difference instead. It's equal to negative the integral of E dot dl from point A to point B. So we have two relationships that connect the electric field to a potential difference. If you're looking for the potential difference, you can start with the electric field and use this integral to get to it. On the other hand, if you happen to know something about the potential difference, you can use this to solve for the electric field in a given region of space, okay? And we're gonna do an example with this in just a second. In fact, like almost right now, I just wanna point out one thing here. This gives us some alternate units for electric field. Taking a look at this equation, in the numerator I have volts, and in the denominator it's just a distance, so it's meters, okay? Previously the electric field was newtons per coulomb. It can also be volts per meter. So this can also be volts per meter. Either one of those is equally valid. So let me show you a little something about how this works. We're gonna go forward 2 slides and we have an example of this relationship between the potential and the electric field. So in this particular case, you can see we have a spherical conductor. So imagine a conductor, we've put some charge on it. All of that charge will be on the outside. We've learned how that works, which means that the electric field will look like this. If I put a positive charge anywhere near it, it's going to be pushed away radially outward. We have learned how to take a situation like this and use Gauss's law to get an equation for the electric field. We learned it looks exactly like what you get for a point charge. So I'm going to go ahead and just write that result down. And again, this comes from Gauss's law in the last chapter. So the electric field, specifically outside this conductor. What's the electric field inside? 0, right? In the conductor will be 0. So the electric field outside is going to be 1 over 4 pi epsilon naught times Q, the total amount of charge that's on the surface, divided by r squared, which is our distance away from the center of the conductor. And you can also write that as kq over r squared if you like that notation better. There have been a few questions about that. K is the exact same thing as 1 over 4 pi epsilon naught. Just depends on which terminology you prefer. You're probably thinking, K. K is easier to remember. It's one thing. Well, true, but there are problems sometimes where having the 4 pi epsilon naught lets you cancel some of it out, and it gets even simpler than K, so either one is perfectly okay. So, okay. Did you catch that? I heard it. I don't know if you did. Either one, K or not K, is okay. I need to go home. That's all there is to it. So, delta V is equal to VB minus VA, and we just learned it's equal to negative this integral from A to B, E dot dl. Notice my integral this time, a couple of things. This is a path integral. This dl is a little segment along a certain route that we're going to take. It goes from a point over to another point. It's a path integral, not a surface integral. Also, we have a dot product in there. You might remember the dot product is something like this. It's the magnitude of both times the cosine of the angle between them. It essentially means that we're going to go along a certain direction, and we're only going to use the electric field components that are parallel to that direction, okay? So in this particular case, take a look over on the left-hand side. We are going to integrate from one point outside my conductor over to another point outside the conductor, okay? Essentially right along one of the electric field lines is perfectly fine. So you can imagine that if I'm looking at DL, which is a little piece of the path between point A and B, at all points, it points in the exact same direction as the electric field. So this dot product E to DL cosine theta, Well, the cosine theta is just going to be 1, and this is just going to be E times dl. Okay? So let's go ahead and simplify that just a little bit. Ooh, let's rewrite this. Oops, that's the pointer thingy. Go away. So this is just going to be minus a to b E dl. Okay? Again, I can make that simplification because E and dl point in the same direction. We have an equation right above for the electric field in this region of space. So I'm going to take it and plug it in. So that means now we have delta V is equal to minus integral from point A to point B, 1 over 4 pi epsilon naught times Q over R squared. And I'm going to change the dl to dr. What's the R direction? Well, it just is along the radius pointing outward. That's the same as the L direction in this particular case. Looking at that, the Q and the 4 pi epsilon naught are all constants. So I can pull those out of the integral. And now I've got minus Q over 4 pi epsilon naught integral A to B 1 over R squared dr. And that's an integral you should be able to do. So let's write that out again. And let's see, that's going to give me something like this, negative 1 over r. And we're going to evaluate that from RA to RB. So point A is distance RA away from the center, point B is distance RB from the center. So let's go to the next step. Let's see, now I've got minus Q over 4 pi epsilon naught. And then inside here, we're going to have minus 1 over RB. Minus a minus, so that'll give me a plus 1 over RA. And then I'm going to pull this negative sign inside here just to simplify a little bit. So that's going to be Q over 4 pi epsilon naught. And then we're going to have 1 over RB minus 1 over RA. Let's take a deep breath and see if you have a question. By the way, here in just a little bit, I'm going to give you a problem to work again so you don't have to listen to me talk for 75 minutes. Because I know it's exhausting. I don't like to hear myself talk for 75 minutes. Does anybody see anything up there that's a little confusing or part of those calculations that don't make sense? We are using a known electric field in our equation to sort of convert it over into a potential difference using this connection between these two concepts. Now, I'm going to make a quick simplification. We are going to let RB go very far away. We're going to let RB go very far away. So we're going to go from a point relatively close, RA, to some point that's very far away from my conductor. Okay? Remember, if I get very far away from any charges, then at that point, we could say that the potential at point B is 0. Okay? Far, far away from any charges, the potential at that location is going to be 0. So remember that on the left-hand side of this equation, I have VB minus VA, which is delta V. So VB is going to be 0, and RB is infinity, so that's 1 over infinity, so that term is going to be 0. And then I've got a negative sign on both sides, so those will cancel out. And we can say that the potential at point A, which is just some point outside the conductor, any point outside the conductor, some distance away, is equal to, let's see, Q over 4 pi epsilon naught R A. So if you are some distance on the outside, whatever that distance may be, okay, you can find a value for the potential at that location near some conductor that has a charge Q on it. Of course, if I make RA get big enough, right, if I get very, very far away, this gets larger. As I get farther away, the potential is dropping. So if I get in an infinite distance away, the potential for that point would be 0 as well. Okay, let's see. Good. Got more slide on the next place. There are 2 more parts to this that we're going to do really quick. That's the long part. All right, let's go over to this and say, let's find the value for the potential at the surface of the conductor. So in other words, we're going to say that R is equal to R0. If you go back and look at the diagram, they labeled the radius of the conductor as R0. So we'll just say that R is equal to R0. Don't think about this too hard. We just found the equation. V is 1 over 4 pi epsilon naught Q over, last time it was RA. Well, now I'm just going to let that be R0, which means it's 1 over 4 pi epsilon naught Q over R0. I'm not sure why that was even a problem. Agreed? Don't you wish they were all like that? We're just picking a value for R and plugging it in. And then finally, find V at a point inside the conductor. Any thoughts? It's a quick answer. Not as quick as you might be thinking, but quick. So in other words, we're looking for a place where R is less than R0. Keep in mind that in a conducting material, the electric field is equal to 0. If the electric field is equal to 0, then we can also say that delta V is equal to 0. Delta V is equal to 0. And that's between the surface and any point inside. If the change in potential or the difference in potential between the surface and any point inside is 0, well, that just means that this answer applies everywhere inside. V is equal to 1 over 4 pi epsilon naught Q over R, where R is less than R0. I like parts B and C of this problem because, well, the answers come kind of quickly. Let me label these B, C. I'll go back over here and call this A. So take a look at the graphs over on the right. Electric field and potential at different distances from the middle. We can see the graphs of the things we just found. So first of all, notice that the potential decreases as 1 over R as I get farther away. This whole thing is proportional to 1 over R. So the biggest it's ever going to get is when I'm really, really close, right at the surface, and it turns out it has that exact value everywhere inside, and then it falls off proportional to 1 over R as I get farther and farther away. That's what the potential is doing. The electric field, on the other hand, remember our electric field equation is proportional to 1 over R squared. And we saw that right there at the top on this slide, right? 1 over 4 pi epsilon naught Q over R squared. So we know as we get farther and farther away from the surface, the electric field is decreasing according to 1 over R squared, but the electric field inside is nothing. So you can see this drops immediately to 0, and everywhere inside the conductor, there's no electric field at all, even though there is a potential at all those points. Okay? So we see something here about the relationship between the potential and the electric field. Does anybody have any questions before I ask you a few of these multiple choice questions and then give you a problem to work? I'm going to give you another Gauss's law problem because I've just seen the looks on your face, the love that you have for Gauss's law. Like some of you have already had the word Gauss like tattooed on various limbs, you know, because you're just like, oh, Gauss's law. Just so in love with this whole idea. I understand. I have 6 Gauss's law tattoos. Yeah. No. Okay, next slide. Next slide. I'll give you a second to think about it. What do you think? You have a question?
Yes.
Yes.
So, just to clarify, the potential of a conductor is equal and opposite on the inside than what it is on the surface.
Equal and opposite?
Yeah, so what I'm not understanding is because the overall difference in potential is 0.
This is the difference in potential between this point right at the surface and any point on the inside. So the difference is 0, which means it doesn't change. It's a constant value.
Okay.
Okay? Anybody have any votes here? It says 1, 2, 3, 4, 6. The answer there is 1. If you just think about it as how much opposition you're going to face, if I try to take this positive charge and push it this way, well, that's going to be harder than trying to push it any other direction because I'm going sort of directly upstream, right? It feels a force from the electric field this way, and I'm going to be directly opposing that. So that's going to take the most work from me to try to move it in that direction. But there is a direction where perhaps it is 0 work. I don't know why there's a box over there on the left. That's kind of strange. A strange remnant of something. 1, 2, 3, 4, 5. Think about what happens if I go, first of all, here we determined I'm fighting against the force, against the electric field. That's going to be the most work. If I go this way, well, actually the electric field is helping me. That's going to be like the easiest in some ways. It's like, oh, I'm not really having to do anything. It's like moving itself. Here, I'm kind of going sort of like against, but not fully against the force that's fighting against me. Here, I'm not working against the force at all. I'm going perpendicular to the force. So in that particular case, I'm not doing any work trying to move the charge from point P over to 3, okay? And that is the last of those, which means it's time for me to give you all a problem. Does anybody have any questions about today's stuff before we revisit Gauss's law once more? No? All right, so okay, good afternoon, everybody. How are you? Where is everybody? This class just keeps getting smaller and smaller. What is happening? Are they getting scared? Extra credit for being here. Yeah, that does make a lot of sense. I'm really feeling what you're saying right now. Yeah. Extra credit for you all. Or we should send out an announcement telling like everyone that the exam is moved, you know, except only the people who are here will know that it's actually not. That'd be terrible, wouldn't it?
Send out an announcement with the answers to the quiz today.
The answers to the quiz today. Well, that doesn't really benefit you guys at all. You know, it just makes the other people freak out an awful lot. Huh. I don't know. We'll think. I feel like there should be at least a small prank
Yeah.
on the other people. Yeah.
So you guys have a review session that they have to go on Thursday.
Yeah. What if maybe the exam first page for just them is a drop form? Just the front page, that's it, drop. And then all of you, you know, like the ones who are normally here, I'll be sure not to give you that exam. And then they'll be freaked out a little bit. Yeah. And the rest of the pages are just blank. There's nothing else there. Just a drop form. Ideas. I'll think about this. So our exam is next Thursday. We've got a week and 2 days. So I think all of us need to just ponder that fact and how somewhat, I can tell you're disturbed. You're already in prayer or something. I'm not sure what's happening back there. So a couple of things that I want to say about that. First of all, we are wrapping up our 3rd chapter. So I get these chapter numbers confused. 22, 23, and 24, I think are the right chapters. They've changed the chapter numbers or something, and things are confusing. So this chapter on electric potential will be the last chapter that we have covered on this first exam. That's not to say that, excuse me, I think I need to move. This a lot of people are deciding to come through there, which is fine. That's not to say that we won't cover additional material before the exam. I'm going to see how that kind of works out because we might need the time. But I want to make sure that you have all the material that's going to be on the exam like a week in advance, okay, instead of presenting new things that are on there. So I'm thinking that we might actually be able to finish chapter 23 today or come really close, so it might dip into Thursday just a tad. After that, I would like to take some significant time to review and do practice problems and that sort of thing in class, and I need your help for that. So if there are topics that you're just like, please explain that again, send me an email that says, please explain this again, and I'll try to take time to do that. If there's a problem that you'd like to see worked again, or a homework problem that you're like, I need to know how to do this, or just some other random problem in the text that you think might be important, maybe it's an example or something, you're just like, please show us how to do this. I will take your emails and try to assemble probably about a class and a half, if not 2 full class sessions of just repeatedly going through things from chapter 22, 23, and 24, okay? So the sooner you send those emails, the more likely it would be that I can actually work those in. If you send me an email 10 minutes before class, I'm sorry. That's probably just not going to happen because I need a little bit of time to prepare, okay? So let's see here. Things closed down, so we need this file. That's what we're looking for. Good, everything is back. This means that the exam is going to break down really quite nice as far as the materials that we have are going to be like highly connected to each other. On the syllabus it says we're supposed to do 1 more chapter before the exam that we're not going to do. We kind of, I don't know, it's kind of off the reservation just a little bit. It's out to the side. It doesn't really connect with those first 3 chapters as well. If you really think about what we've been talking about, we dealt with force, field, and potential. Those will be the 3 big things that you're going to have to focus on for the first exam. Force, field, and potential. Okay? We are going to talk most of today about potential, although some of it is still going to connect back to electric field. I really hope that some of the graphics that we have today starts to give you a feel for how electric field and electric potential are all intertwined and connected, and you can't really separate them. So I'm going to take a good bit of time sort of explaining those diagrams and letting you try to absorb them, but that's later in today's class. So first of all, I want to do what is a relatively basic example dealing with potential. And I'm sorry that's a little hard to read. It says that there are 2 large parallel metal plates carrying opposite charges of equal magnitude. So I'm just going to draw sort of a side view of this and say that these are 2 large metal plates of equal magnitude but opposite charges. So we're saying that one of these is positively charged, one of these is negatively charged, And this creates an electric field in between that looks something like this. Because if I drop a positive charge anywhere between those two plates, it's going to be pushed away from the top plate and down toward the bottom plate. That defines the direction of the electric field. Notice it says they are separated by a distance of 45 millimeters. So we're going to say that this distance is 45 millimeters. And the potential difference between them is 350 volts. So we could say between these 2 points, we have a delta V, a potential difference of 350 volts. As a bit of a refresher, remember what this means. When we're talking about potential differences, we are saying that regions, let's say sort of up here near this plate, have high potential. There's a lot of reason for a positive charge dropped in that region to move. Just like if I take a mass, up here is a higher potential than near the ground, okay? Because there's going to be more potential energy in that region if I put a charge there. So this is where I have high potential, and this is where we have, down here is lower potential. From the standpoint of a positive charge, which is how we define all of these things. Now keep in mind, it's not like the way I've drawn it where just the top is high and just the bottom is low. It's like a gradient, okay? It's a slope. It's ever changing as we go from the highest possible potential and then to a little lower, 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 until the lowest possible potential at the bottom plate, okay? So a few different things we're going to ask, and I'm sorry that these questions aren't up here. I'm just going to go ahead and write them. So part A, find the magnitude of the electric field between the plates. And the problem also says that it will be a constant value. The value is constant. Find the magnitude of the electric field between the plates. If you take a look back in your notes from last week, you might find an equation that will allow us to get to this relatively quickly. There's an integral equation that we don't have to use here because the electric field is constant value, but you could maybe take that integral equation and look at a more simplified version and tell me what you see. Does anybody happen to see an equation in there that relates the electric field and the potential difference? Anybody? If you think you see something, shout it out. It's just something divided by something else. Yeah. If I'm just looking at the magnitude, it is the potential difference divided by the distance over which that potential difference is occurring. Remember, it's the slope. The electric field is essentially the slope of the potential, okay? Specifically, if we weren't looking at the magnitude, it would be the negative slope, all right? So in this particular case, this is a relatively easy calculation. We've got 350, and I need to convert that millimeters into meters, so that's 0.045 in the denominator. You should get 7778. And you can express that two different ways. We have two different sets of units for the electric field. I could use what's here. We've got volts in the numerator and meters in the denominator, and that is perfectly good. Newtons per coulomb is also a unit that would work. Part A, you like part A, right? Part A is good. You can do part A. Part A is pretty happy. Part B, it's not going to get any worse. Next thing, we're going to find the magnitude of the force on a charge of Q equal to 2.9 nanocoulombs. So we're going to take a charge and put it in this region of electric field and see what force it experiences. How do we find the force from the electric field? F is equal to what? Careful. Connected to the electric field. That's the value we have. I'm hearing the equation for like the electric field created by a point charge, which is what I think I was hearing. How is the force related to the electric field? Something times something.
Charge times the field.
Yeah, it's just the charge times the field. F is equal to QE. So I know the electric field that already exists. I'm going to drop a charge in there and see what force it experiences. So 2.9 nanocoulombs is 2.9 times 10 to the minus 9 coulombs. And the electric field is 7778. And that gets everything in consistent units. And when you multiply those, you will get newtons. You should get 2.26 times 10 to the minus 5 newtons of force on the charge in that region of space. Which brings me to part, let me read this and see which way I want to do this. Let's see, part C. Let's find the work done on the charge. We'll say done on Q. As it moves from the top plate to the bottom plate. I'm running out of space down there, aren't I? So we're going to have to go to the top to answer this, and I'm going to go the long way around. Yeah, this is completely pointless. There we go. Just to amuse myself. Okay? Find the work done on the charge as it moves from the top plate to the bottom. So we're going to pretend that we take this charge and drop it right next to the top plate, and that electric force is going to make it move to the bottom plate. And we're going to find out how much work is done. So you might remember that work just in general is equal to F times D. Yeah, exactly. Assuming that those are pointing in the same direction. If they're pointing different directions, there's also a cosine of the angle between them that you have to deal with. So in this particular case, it's just F times D, and we know the force is 2.26 times 10 to the minus 5, and D is 0.045 meters, once again. You should get 1.02 times 10 to the minus 6, and what are the units of work? Joules. Good. Units of work are joules. This is the work that's being done by the electric force to move the charge. Okay? One other thing that we can quickly find here is, let's see, find the change in electric potential energy. So find the change in potential energy from top to bottom. So again, this is the potential energy that the charge possesses. Remember, potential energy is possessed by the charge. Potential is something that points in space have. Okay? So we can find the change in potential energy by using an equation from last week. Let's see, so delta PE, or delta U is the same thing, is equal to the change in the potential times Q. The change in potential times Q. The change in potential is just 350, and Q is 2.9 times 10 to the minus 9 coulombs. Or you didn't even have to do that, because we already had the answer. You might remember that the change in potential energy is also equal to the work. Okay? So this is another way of coming at the same answer. For that, you should still get 1.02 times 10 to the minus 6 joules. The amount of work that's done is equal to the amount that the potential energy of the charge changes. Okay? And you can punch that in and see that you get the exact same thing. Does anybody have any questions on this particular example? Yeah.
I might have just missed this entirely. What is the units for potential difference?
Volts.
So then, because of the fact that it's force times distance, it's in meters and volts per
times, and volt times Coulomb results in joules.
So both numbers now.
Yeah. Anyone else? Okay, moving forward. You might remember from last semester, and we're not going to dwell on this too much. I will do a quick example. I just want to point out that what we're doing now still ties into things you learned in 220, like conservation of energy. You might have remembered you had something like kinetic energy plus potential energy initial was equal to kinetic energy, and I'm writing that different than maybe you've seen it, final plus potential energy final, right? The amount of kinetic and potential energy that you have has to stay constant. It just changes forms. And we can use this equation as long as there are no non-conservative forces that are sort of taking energy away. So let me clarify this. This is for no non-conservative forces. Okay? And you may have learned last semester about a few different types of kinetic energy. There was like translational kinetic energy, which is 1/2 mv squared. And maybe you learned about rotational, which was 1/2 I omega squared. Does any of these equations look familiar at all? You've seen these before, okay? You might have learned about a few types of potential energy, like gravitational potential energy was m times g times y. Spring potential energy, 1/2 kx squared. I can't remember if maybe you learned about any more. That was probably about it. And sometimes you had problems where you had to like mix all these together and figure out what types of kinetic and potential energy you had and solve for some unknown in there. I want to point out that at this point, this potential energy that we just learned about can be added to this list. So electric potential energy, which is equal to the potential difference times Q. And that should be a V, even though I kind of rounded it off a little bit. You get the idea. Or if we wanted to specify, say, at a single point, and keep in mind when we're doing conservation of energy, it's usually like how much do you have at this point, and then how much do you have at this other point. We might re-express this as, say, just U electric is equal to the potential at that point times Q instead of a difference in potential. So we're able to add to this list of things that you were already working with last semester, and we can do conservation of energy using electric potential energy. In 2 slides, I want to do a quick example that shows you how that works, and it's really straightforward and easy, okay? But first of all, let's take a look at this problem. Again, we've got this apparatus where we have a positively charged plate and a negatively charged plate. We have an electric field in between that points from positive to negative. This is saying that we take a proton and put it right next to the positive plate. We know it's going to get pushed this way. We're going to take an electron and put it right next to the other plate and release it, okay? So we know that they're going to be pushed opposite directions and fly to the opposite plate. When they strike the opposite plate, which one has more kinetic energy? Which one would have more kinetic energy? What are you going to do? Any thoughts? You can vote with your fingers maybe if you think you have an answer.
Both not the same.
Both have the same. Why?
Because kinetic energy is supposed to be equal on both sides.
Close. You're right. Your answer is right. They have the same kinetic energy when they get to the other side. But what is the reason why?
Because initial is equal to final.
Initial is equal to final. Yeah, it basically goes back to this equation, right? they both start with the same amount of potential energy because a proton and electron have the same charge, and they're dealing with the same potential difference. So if they start with the same potential energy and lose all that potential energy as it gets converted to kinetic energy, they have to have the same kinetic energy at the end, okay? So we could say that both have the same initial potential energy. So that would be UI. This is all converted to kinetic energy. And if they start with the same and all of it gets converted, that means they're going to have the same K final. All the initial gets converted to kinetic energy. Okay? So let's do a quick problem related to conservation of energy, and then we're going to jump into what I really want to focus on today. Okay? So let's see. Here we have another problem where you can't read the top line. Beautiful, right? Hopefully you have it in front of you somewhere. It says that there is a small particle that has a charge negative 4.1 microcoulombs and a certain mass. It moves from point A, where the electric potential is one value, to point B, where the electric potential is another value. The electric force is the only force acting on this particle, and it has a speed that's given there at point A. So the fact that it says the electric force is the only force acting means I don't have to worry about gravitational potential energy or any other weird thing that's involved. I just have electrical stuff that we're focused on, okay? And we have two different points, so let's just go ahead and write these out. Here at point A, and here's a different point B. You could think of these as the initial and the final point when I'm dealing with conservation of energy. So I'm going to write down K at point A plus U at point A equals K at point B plus U at point B. And let's see, they told us at this point, at point A, the velocity at point A is 3.9 meters per second. And this is very quickly going to get confusing because we have velocity and potential, and both of them are V's. So let's be a little careful here. I'm going to make this V like smaller, maybe kind of cursive, just to keep track of things. So we also have a potential at point A that is, let's see, 190. And then we have a potential over here at point B that is 620. We are going to try to find the velocity at point B. The velocity at point B. So let's see what happens. At point A, kinetic energy, 1/2 mass times the velocity at point A squared. It has electric potential energy, and that's equal to, whoops, that's going to be plus Q times the potential at point A. And then at point B, we're going to have 1/2 mass times velocity at point B squared, plus the potential energy there, which is Q times the potential at point B. And this should remind you of problems you did in the previous class. It's kind of the same thing. The only thing that's changing is how we write the potential energy. We're not using one of the potential energies you had previously. So we're solving here for the velocity at point B, which just means some algebra must be done, right? So let's see, 1/2 mass velocity A squared plus Q VA minus Q VB. And we're going to have to take that whole thing and multiply by 2 and divide by the mass and take the square root. There we go. Did all the algebra in one fell swoop. No? Did I mess up?
Yeah, VB, the one inside isn't supposed to be there.
VB isn't supposed to be there.
That's supposed to be divided by Q.
Let's see, I've got this one plus that one, and then I'm going to subtract this one over on this side, and then multiply this by 2, divide by mass, take a square root. I think it's good.
But you don't have the VB. How will you plug it in?
Don't have VB.
The one inside. Next
This
to
one?
the- Yeah.
Oh, we do have that one though. It's 620.
Oh, it's,
That's the potential at point B.
oh,
So let's plug these in and make sure that we're all on the same page as far as what the numbers are. So the mass, they said, was 1.2 times 10 to the minus 4 kilograms. The velocity at A is 3.9, so it's 3.9 squared. Plus, and let's be a little careful here, that's a negative charge, so minus 4.1 times 10 to the minus 6. To convert that to coulombs, times the potential at point A, which was 190, minus a minus 4.1 times 10 to the minus 6, times 620. Make sure we get all of that inside those brackets, and divide by the mass, which is 1.2 times 10 to the minus 4. All of that equals the velocity at point B. And it should be 6.68 meters per second. It's sped up. Think about that for a second. It's going faster when it gets to point B. Does that make sense? Like, I'm not sure if it makes sense. Is it supposed to make sense? It should make sense. Tell me this, based on these potentials, higher potential, lower potential, which direction is the electric field between points A and B? It's up, down, left, right, in, out, sideways. Which direction does the electric field point? Electric field points from high potential to low potential. High potential to low potential. So that means the electric field is going this way. Electric field is going that way. So does it make sense that a negative charge would speed up as it goes the opposite direction? Yes. Right? A positive charge would feel a force in the direction of the electric field, which means that if it had a velocity here, it would feel a force and go faster. Okay? It like wants to go in the direction from higher to lower potential. A negative charge is going to do exactly the opposite. A negative charge feels a force the opposite direction. Okay? So if it has a certain velocity here, well, it makes sense that going against the electric field, it's going to go faster because it feels a force that way, okay? And notice, in case you missed it right here at the top where you can't really see, that is a negative charge that we're dealing with, okay? So if we dropped a positive charge there, we should have found a lower velocity here, and you could try that. Just put in positive values for the exact same charge, and you should end up with a velocity that decreases instead. So you could try that for your own instruction if you wanted to, okay? Now we're going to get to what I really want to get to, all right? We talked about a few different things over the last few chapters. In the first chapter we covered, we dealt with the electric force, and at some point in that chapter we wrote out an equation for the electric force that's created by a point charge. Does anybody remember what that equation looked like? Or the equation, I guess it was between 2 point charges. The electric force. I think I heard it out there. We could write it as K, Q1, Q2, good, over R squared, right? That is for a point charge, or for dealing with point charges, 2 point charges. Both of them feel the same force on each other, okay? Then in the next chapter, we found the electric field created by a point charge. Does anybody remember that one? K times what? It's just Q over R squared. Okay, that's been our sequence so far. Each chapter has had one of these, sort of. It's like force, we got with that. Then we move to electric field, again, just dealing with point charges. Now you can see there at the top, we're going to look at the electric potential that's created or comes from a point charge. So we can write that as V. And it turns out, if you look back at our last lecture, we did a bunch of calculus and actually found this answer already. So I'm not going to go through this again. We just didn't specify it at the time. It's simply KQ over R. So we get rid of that extra R that's in the denominator. And again, this is potential that is created by a point charge. I don't want you to forget, though, the key thing about potential is that it is a scalar. And you will find when we do some problems here in just a minute that it makes calculations so much easier. Like delightfully easier. Like some of you might just like swoon with delight. You're going to be like, this is fantastic. Why can't we do it this way all the time? Much of the time you can, because we have connections between potential and electric field. So if given the option, and I ask you to find the electric field, you can be like, ooh, if I know how to do that by finding the potential first, my life is a lot easier, okay? So this is a scalar, which brings me to the first diagram, and what I put up there, I didn't actually want to talk about, we did that already, which is these two diagrams, and I need a moment to explain what we're looking at, okay? Notice at the top it still says electric potential from a point charge. We are still using this equation, okay? So a couple of different things about that equation. K is just a constant. We know that. It's 9 times 10 to the 9th. Q can be positive or negative, which means I can have a positive or negative value for the scalar potential. R, being in the denominator, is just telling me that, well, it's going to get weaker. There's less potential as I get farther away from the charge. And it falls off according to 1 over R. You could draw a 1 over R curve, okay? So looking here on the right, we've got a graph of the electric potential in the region of space near a positive charge, and then we've got the same thing in a region of space near a negative charge. Now the way these diagrams are drawn, I both like them and dislike them because if you notice the axes, like stare at that for just a second, it's like where is X and Y exactly and where is the charge? I understand it's confusing. So you can see that first of all, 0 on the x-axis is here in the middle, and then you got to go all the way up to the top to figure out where 0 on the y-axis is. Ugh. Yeah, it's a mess. The origin actually sits kind of like down here in this bottom plane. It's trying to tell you that like this is one axis and another axis looks sort of something like that. Okay? So y is, positive y is this way, positive x is that way, but my xy plane is sort of in the base of that cube. Does everybody see that? Maybe a little bit, okay? The positive charge that they're talking about is at the origin. So right there we have positive q. It's sitting at the origin. All of this other stuff that's graphed around it are just the numbers for the electric potential, and they're graphed on the z-axis, okay? So essentially what someone did was take this equation and just basically plug in a single charge of maybe, they just put in like a 1, and then put in something like the constant for k, and then just went to every coordinate r and decided to calculate the potential and see what that is. Clearly that would be a lot of work, so someone just generated the whole thing on a computer, okay? When you do that, well, it makes sense that if I put in very, very small values for r, I get very large values for potential, okay? And you can see on this diagram, anywhere when I'm really, really close to 0, 0, notice what the potential is doing. It's basically going to infinity as I get really, really close to that charge. All right. If I get farther and farther away from the charge, well, according to this, if I get farther away, the potential is going to drop and it gets really weak as I get farther away. Okay. So this is a way of sort of visualizing what the potential looks like. It's positive and big near a positive charge, it gets smaller as you get farther away. But it's positive everywhere in the region of space around it. Okay? Let me pause there for a second, take your question.
So is this only for a point charge? It's not for that scenario where we have the two plates and we put something in?
Nope. This is just a single point charge that's sitting somewhere in the XY plane, just all over. All right? We could graph something similarly in 3 dimensions, but boy, that would be a bear to try to look at, right? We would need a video and be able to like rotate it and stuff to try to look at that, okay? These are just the values at different XY positions in that same plane. Now I want to zoom in on this just a little bit. There's some other lines here that are actually instructive. Whee! All kinds of fun, okay? These green ones, these circles that go around, we're going to deal with those later in today's lecture. So just keep in mind, those green lines are there for a reason, okay? These purple ones that are pointing out, they actually represent something. Let's draw them in here. Oh, what color to go with? Something that contrasts with it a little bit. Oh, I shouldn't use green because that's just going to confuse. This line represents, believe it or not, the electric field. Now let's step back and think about that a little bit. All of these lines around here represent the electric field around that charge. Imagine something with me, if you will. Take this diagram and let's just flip the whole thing towards you so you're like looking down on top of this cone shape that's there, okay? What are you going to see if you look down on top of it? See something that looks like this. Right, I would just see a positive y and a positive x. I would see my positive point charge in the middle. And I would see all of these lines sort of going out from it in all directions. I wouldn't see that curve. I would just see all these lines just going radially outward, right? That's what we learned the electric field for a positive charge looked like. Agreed? Okay? So that's represented here on this diagram. What is being added to that is the slope quantity and how it relates back to the potential. Remember we said that the electric field is the negative slope of the potential. Look at the diagram. Like what if we kind of went like, you know, like right here and looked at one of these lines that I said is the electric field? Well, that has a slope, right? The potential values, the actual numbers for potential here are changing and they're dropping rapidly, okay? They're also going down. They're becoming less. I could go right on this line, right on the side of this curve and find the slope. It would be a negative slope, and that negative slope is how quickly the potential is changing. That is the electric field. Do you see how these things kind of tie together just a little bit? I know it's a lot, but if you can like grasp this slide, it explains a whole lot of everything that we've been doing in this chapter and in the last, okay? Let me represent this one more way. Think about what electric field and potential mean. They're sort of like two sides of the same coin. One is a vector way of describing it, one is a scalar way of describing it. For an electric field, we say that that is the direction a positive charge would get pushed, okay? So if I'm dealing with a positive charge being near another positive charge, I know it gets shoved away. Well, that's what these electric field lines are telling me. They're saying, like, put a positive charge there anywhere, it'll get shoved away. I can also represent that as a potential. Positive charges want to go from high potential to low potential. So what if we sort of relate this back and pretend like this is a physical hill and there's gravity? You could imagine if I put something right here and I was pretending that this whole thing is related to gravity, what's it going to do? Whee, right? It's like going to ride that slope down and be pushed away. Is anything really there that's like a hill? No. But you can think of it sort of in those terms. It wants to ride that potential from a high potential and go over to where there's a lower potential. That's what the object wants to do. Just like something in gravity, it wants to go from a high potential down to a lower potential. It's just that this is kind of the only way we can visualize it, because just like I can't see, like there's no like potential that's here. It's the same thing when I'm dealing with the region around charges. There's nothing physical there, but there is an impact. There's a presence that makes things want to go from high potential to low potential. Okay? Do you see the electric field, the electric potential, and how that slope there connects the two together? If you understand it like half, that's pretty good at this point. You're going to have to sit with it a little bit maybe to kind of absorb it a little more. Let me slide over to this one. We'll talk through it one more time, and then hopefully everything kind of comes together. So this time we're near a negative charge. What does a positive charge want to do if you put it near a negative charge? Right? It gets drawn to the negative charge. Okay? So in this particular diagram, this time, for whatever reason, they have decided that the X and Y axis are up here in the top part. I'm sorry that those are backwards like that, but maybe you get the idea. So this is positive Y, this is positive X, and the origin sits right there in the top box of that cube. Okay? So this is where there is a negative charge. It's sitting right there in the XY plane, which is at the top. Okay? So you can imagine that if I were to bring a positive charge somewhere nearby, what if all of a sudden it's like, oh, a little positive charge kind of wanders into this region? Like, as long as it's like way over here somewhere, like, that's fine. You can just set it there. It's no big deal. If it gets too close to that negative charge, though, the negative charge is going to take over. And you can sort of see that represented by the way they've drawn the slope, right? If this positive charge gets a little too close, it gets sucked into the hole, okay? That's representing it being pulled in by the electric force that we draw as an electric field, and you can see that effect drawn in the potential as a potential hole, okay? Yeah.
So is this scenario synonymous with like gravity?
Same kind of idea. We can draw pictures like this for gravitational potential as well.
But it would only be the one on the right because there's no repulsion.
Exactly.
Okay.
Yep. And maybe you've seen diagrams like this with like black holes and things kind of like that. It's the same exact concept. The math is all basically identical. So if we look at this diagram, again, you see these lines. Now the electric field, remember, points inward for a negative charge, so that any positive charge that comes nearby gets drawn toward it, okay? Notice also that all of these values of potential, look at this vertical axis, they're all negative, right? It's a scalar. If there's a negative charge, it creates a negative potential everywhere around it. Who's got questions? How much fun is that? This is like the best slide we've done all semester so far. Yeah.
Do the actual lengths of E determine its magnitude?
Yes, but those aren't really represented here. So if we were to like carefully draw the electric field vectors, they would be very long close to the charge and shorter as we get farther away. None of that's really drawn there. Who else? We're not really done with this idea yet, okay? What I want to do now is, like, on the next slide, we're going to do an electric potential calculation of our own, okay? I'm going to show you how easy this can be. I'm going to ask you a few questions. We may skip that for today because I want to get to these diagrams as well. You might start to recognize that they, in some ways, look familiar to what we just did, okay? So let me start with this. 2 point charges. Oh, look, it's actually all on the screen this time. Notice the first one is positive, the second one is negative, and they are placed 1/10 of a meter apart. You can see that drawn here in the diagram. We've got a positive charge Q1 and we've got a negative charge Q2. Point A is right in the middle between them. Point B is in that position kind of closer to Q2 than it is to Q1. We are going to try to find the electric potential at point A and at point B, okay? So let me scroll forward to make sure I have all the right answers in front of me because that's just nice to have, okay? If I want to find the electric potential at point A that's coming from point charges, all I have to do is find the electric potential from charge 1 and add it to the electric potential from charge 2. No vector considerations at all. Yay. Be happy. No vector considerations at all. Yay. That's better than nothing. No vector to worry about at all. None. No vectors. Yes, exactly. If we tried to do this, and I'm going to show you in just a second, and tried to find the electric field here, you're going to be sitting here working on it for a little while, okay? Because there's like no symmetry where things cancel out or anything. Like you just have to like brute force your way through the entire problem. So if I want to find the total potential, we're just going to write K times Q1 over R1 plus K times Q2 over R2. D2. It's weird how that happens. So the K's are the same. I'm going to go ahead and factor those out just to simplify the math a little bit. And we've got Q1 over R1 plus Q2 over R2. And let's plug the numbers in. And then we're done. So K is 9 times 10 to the 9th. Q1 is positive, and notice it's listed as nanocoulombs. I need to convert that to coulombs, so it's going to be 2.3 times 10 to the minus 9. And R1 is just the distance we are away from Q1, and you can see that that's 0.05 meters. Q2 is negative, so I'm going to go ahead and write the negative sign there, and then it's 6 nanocoulombs, so 6 times 10 to the minus 9, and it's 0.05 away. So the total potential at point A is just that, and interestingly and weirdly enough, it's negative 666 volts. You gotta love that, right? Yes, 1,000 times yes. Remember how we found the electric field? Yeah, like if I want to find the electric field at point A, like first of all, I have to be like, okay, let's say there's a positive charge there. Which way would it get pushed? It would get pushed this way. So E1 goes here, and a positive charge would be drawn to the other one, so I would have E2, and it would go that way. So I would have to consider the fact they're pointing in the same direction, and then yes, I could use K Q1 over R1 squared plus K Q2 over R2 squared, and that would be fine because they're pointing in the same direction. That would give me a total electric field at point A. And we would find that it points, we'll say to the right. So that one wouldn't be too bad for finding the electric field, okay? What about the electric potential and electric field at point B? Well, that's not terribly bad either. So it's just going to be V1 plus V2. So once again, this is going to work out to be K times Q1 over R1 plus Q2 over R2. Do you hear that? Like, you know, it just kind of like you hear R2 and you can't help but hear D2. It's just one of those things. You know, I don't know what the deal is. So let's see. Some of the numbers have changed, but otherwise everything is fine. So this is 9 times 10 to the 9th. Q1 is still 2.3 times 10 to the minus 9. Our distance here has changed. It's now 0.08 away. minus 6 times 10 to the minus 9, and this distance is 0.06, just looking at the diagram. For this, you should get negative 641 volts. Again, that's not too bad, right? Imagine what you would have to do with electric field, though. Yeah, I don't want to. You know, we're going to. I don't want to, but we're going to, okay? So imagine there was a positive charge there. Well, it's going to get pushed away from Q1, so I'd have an electric field that points that way. And it would get drawn toward Q2, so I would have an electric field that goes that way. And then I'd have to find those angles and break them into components, and it'd be terrible, okay? You should be able to do that, though, in case I ask you how to do it next Thursday. It would be a really nice problem to say, like, hey, here's some charges. Find the electric force, the electric field, the electric potential. Like, that kind of ties everything together. That should be the whole exam. That'd be fantastic. Hello, get my picture taken. And nice to see you. Yeah, this is my work. Fantastic. Yeah. I'm wondering, at this point, like, how many pictures are out there with me like this and a screen behind me? There's got to be a billion. Sadly, no one's tagging me on Instagram. You know, I don't know what's out there. Who knows? But I bet I look terrible in all of them, right? Like, I should know. I should just immediately be like, yeah, but no one ever gives me the chance. So, electric potential at point A and point B, that's how it's done. That is wonderful, don't you think? You can do this. Yes? Oh, you can do it. You'll be fine. So moving on. I want to skip a few slides to make sure that we cover the material, or at least the focus on the material, and then we can always come back and answer a few of these questions. So let's take a look at these diagrams. These diagrams introduce those green circular lines that were on the other one. Notice these are color matched to what we had before with the big, you know, the hole and the peak. We had the purple lines that were representing the electric field, and there were these green circles that I said we'd come back to later. These are known as equipotential lines. And equipotential lines is really just a simple, well, not a simple, but a complicated word to describe locations where the potential is exactly the same. So if you go back and look at our equation, V is equal to K, Q over R, well, if I'm dealing with a certain charge, the potential will be the same if R is the same. Right? If you're the same distance away from a charge, everywhere that I'm the same distance away, I'm going to get the exact same value for the potential. So that's what these lines are trying to show. Notice they're circles. If I'm around a positive charge, well, if I go out to some distance and I go in any direction that distance away, this equation is going to give me the exact same answer for the electric potential. Or I can go to some other distance away, and everywhere on that circle, I'm the same distance r away from the charge, so I get the same value for the potential. Okay? This might remind you of another type of map or drawing perhaps you've seen, especially if you like to hike, and maybe if you take hiking seriously, which I don't by any stretch of the imagination, because walking, and especially walking up and down hills, is exhausting. There's a picture of me that I like a lot from about 5 years ago, where my wife and I were going to go for a walk. Well, the walk started at the donut shop, right? So there's me on the trail, like, let's walk! And I've got a donut, and we're heading down the trail, and everything was fantastic. It should have also ended at the donut shop. We needed to go around a closed loop and start into the same place, and life would have been happier. But, you know, my wife got me to walk by giving me a donut. It's like, I might as well be a puppy. That's really kind of what happened. It's like, you know, Nathan, come walk. I got a donut. You know, I eat a donut and everything's happy. So a topographical map is a map that shows us something about gravity and where gravitational potential is the same. So maybe there's a map of like a hill or something. Let me go over here. And maybe it's a hill that looks like this. It's like, whee, there's a very sharp hill. And then maybe over on this side, it's, you know, kind of slopes down something like this. Okay? And this is a side view of that hill. What am I writing? I don't know anymore. Side view. Well, a topographical map shows us something about elevation by relating it to gravitational potential. So you might see something that kind of looks like this. I don't know, maybe there's like a circle like this. And then over on this side, it kind of does something like this. And then these are like really close together. And maybe it looks kind of something like that from the top view. You've seen this, right? Okay. That's trying to tell you something about potential, and these lines are equipotential lines, even though they don't call them that. Okay? Each one of these lines means that there is no change in potential. It means there's no change in altitude. So in other words, if you're like me and you want to go on a hike, right? You want to look at one of these maps and figure out where one of these lines is located and stay on it. Okay? Because if you just pick this line and go around this way, assuming there's a path that follows that, you never go up or down, you stay nice in the easy level and everything is fine. Okay? What you don't want to do is like go perpendicular to these lines. See, this indicates that your slope or your potential is changing rapidly, okay? The way that they draw these lines is what they're saying is that every separation is the same change in elevation. So maybe a separation between lines here represents, I don't know, 100 feet. Well, this means over a very short distance, it's like 100 feet up, another 100 feet up, another 100 feet up, oh, I'm at the top. And I had to do that in a very short horizontal distance. This would mean like from here to here is 100 feet up. Ah, that seems a little better. And another 100 feet up, and another 100 feet up, and so forth, okay? So this is an easier slope going here than it is there because the potential isn't changing as fast, all right? So a topographical map is really what we're looking at here. It's just the topography isn't elevation changes, it's potential, and specifically electrical potential changes. Now, think about this and think back to that first three-dimensional diagram we looked at. Remember I said look down on the top of it? This is the top view of that diagram. You can actually imagine this as like a peak that's coming out towards you, okay? The positive charge sits near the middle of that peak because that's where the potential is the greatest, and then the potential falls off as you get farther away. Notice they've actually drawn in the electric field lines this time and say that they push away. Also, notice the way these equipotential lines are positioned. They're really close together when I'm close to the charge because the slope is falling off rapidly. And as I get farther away, things are getting flatter, okay? Those diagrams on the other page and these diagrams work together. The colors are the same and everything to help you understand potential and electric field. Let's see, what else should we say about this? Oh, well, of course, also, like, where do you want to hike around an electric charge? Stay on one of these green lines because the potential doesn't change. You don't have to fight with or against the electric field by going up or down, okay? There are some more complicated examples here. So here they've just decided to draw a similar thing, but for two positive charges that are close to each other. It's almost like you could look at this and imagine these are two peaks of a mountain, okay? It's like we took this and put another one right next to it. So this is going up to a peak here, and then maybe it doesn't level out all the way in the middle, but there's another peak that's there, okay? Again, well, you can kind of see what the equipotentials are looking like, and also the electric field lines tell me which direction a positive charge would get pushed. But I like the one that's over here on the right. One positive and one negative. One positive and one negative. Think about what that means if I were to graph this as three-dimensional potential. Okay, positive values and negative values. Remember, near a positive charge, this is like a peak that's coming out this way, right? It's like a mountain in this direction. A negative is a peak in the negative direction. It gives me negative values of potential. So it's like I've got a mountain coming out here, and on the other side, we've got a mountain that's more like an inverse mountain, right? It's like a pit or a hole that's going the other way. Can everybody see that? Yes, you can visualize it. There we go. Okay? Let's make sure that this makes sense. Imagine what would happen if I take a positive charge and put it near this positive charge. Remember, it's sitting all the way at the top of this positive potential mountain. Well, of course, it's going to like be pushed away, kind of like it rolls down the potential mountain. And then, well, there's a pit right next door. It's just going to keep on going and roll right into that other pit, right? Well, that's reflected in the electric field. If I put a positive charge here, it's going to get pushed away from this positive charge and end up stuck next to this negative charge. The electric field seems to agree with what we see in the potential map. Whew, it's a lot of stuff. Are you feeling okay? Are you feeling better than you did before? Does this stuff kind of help a little bit? Maybe it ties it together. I don't know. How's our time? Doing pretty good. Excellent. Okay, so let's move forward here once again. Yeah. We're actually not going to do this slide. I changed my mind. And yeah, we're not going to do, no, we are already going to do that slide. Let me leave that in there. But we're going to do that next time. Let's see. So I want to give you guys a problem to work before we leave today. And then we're going to go back and fill in a few of these gaps. You've got basically the material that you have to know for the exam. The other stuff is just some clarification, a few details, etc. But we can finish that up easily on Thursday. Because I want to give you some practice problem on the potential. And let's see, let's just put a slide in here somewhere, and I will write you out a problem. So go ahead and find someone. The potential at point B, which is this point, is supposed to be right on the y-axis. The same two charges at the bottom. What do you think it is? All at once. 0, because I'm in the exact same distance from both of the charges. So both of those terms on the previous slide are going to be equal, just one positive and one negative. So at that point, I get 0 potential. Now you can imagine for a situation like this where I have two charges, I could ask you to find the potential at any point, right? I could say, hey, what's the potential right here? What's the potential right there? What's the potential right here? What's the potential right there? Right here, I could sign like 1,000 million problems, right? If I wanted to, like practice if you want to. Just pick some random place at some distance from the two charges and make sure you understand how to calculate the potential. You should also be able to take two charges and find the force on a third charge somewhere else. You should be able to take two charges and find the electric field at some other point. These are all things that we've done in these first 3 chapters. Electric field, electric force, and potential from point charges, okay? We're gonna do an example later that's just like that, all right? So moving on, 4 point charges are arranged at the corners of a square. The 2 left ones are negative, the 2 right ones are positive. Find the electric field and the potential at the middle on that black dot. And you can see our answers are not exact. It's just 0 or not 0 for both of them. The electric field and the potential at the center. What happened here exactly? I feel like something occurred here today that like either someone was in trouble and they were forced to sit with this little desk chair thing. Maybe someone had lunch here. I don't know. I kind of want to lecture from this position for the rest of the class. There we go. This is kind of fun. Y'all think about that while I'm over here doing my own thing. Can't help but want to turn around. Let's take them one at a time. Potential at the center of the square. 0 or not? That's good. Nice work. So the 2 answers are either 0 or not. So say the word 0 or not, whatever your answer is. Go. 0. It sounded more like 0, right? So our answers are either that one or that one. And again, that point at the middle is equidistant from two positive and two negative charges. It should add to give me 0. But what about the electric field? Imagine what would happen if I drop a positive charge at that point. Will it feel a force or will it not? Sure seems like it might feel a force, right? You can imagine it's going to be repelled by both of these, and it's going to be drawn to both of those, right? It's going to feel a force toward the left, at least roughly speaking. So the potential here is 0, but the electric field there has some value that points to the left, because I know a positive charge would feel a force in that direction. So our overall answer is this. There is an electric field at that point, but there's no potential. How's that possible? One second, I'm going to change slides and see if there's something here that might help. Going back to, which one? Maybe this one would help. Take a look at that right diagram. Remember we talked about this being like a big mountain that's coming out? And over here, this negative charge represents a negative, like a hole of potential, right? Well, right in the middle, you would have a potential of 0. Agreed? It's kind of like, that's kind of like ground level. Here I have a mountain, here I have a valley. Right in the middle is like exactly 0, not positive or negative. But right in the middle, there is an electric field because something's going to want to go from high down to the low point, okay? There's still an electric field in the middle because there's a slope in the potential, where the negative slope of the potential is the electric field. So you can almost imagine this, like if I were to flip this sort of sideways like this, like it's going something like this. I'm going from one peak in the potential that's positive down to a valley that's negative. There's a point in the middle that's 0, but the potential is changing and has a slope through that point. If there is a slope and the potential is changing, well then there is an electric field, okay? If you're trying to think about how the electric field and potential relate, like try to get some of this 3-dimensional figure stuff in your head. Try to relate it back to that. Imagine potential as these mountains and valleys. And I think it helps a little bit trying to understand the electric field. Maybe it does, maybe it doesn't, who knows? So back to this one. Electric field is not 0, it exists. The potential though is 0. Yeah.
Is the force being exerted by both the positive charge and the negative charge the same?
The force being exerted by both,
Like if we see it in 2 separate systems.
yes, but it's also dependent on the charge that's feeling the force. So a given charge would feel the same force from both an equal positive and negative charge, just in opposite directions. Yep. Okay. Yeah.
Even though that is like neutral, since they're both like giving off the same, it's still like the force is at 0. That's why we have to answer it as like not equal to 0.
As far as in this problem? Yeah, if there is a force, then there is an electric field. And there will be a force if you can imagine repulsion and attraction being something that's happening at that point. Okay? There is one new thing here on the slide. One new thing. There's going to be something a little new later, but actually we've already kind of talked about it. So electric potential from point charges is what we just finished. We just used KQ over R if I have a point charge. But sometimes I have too many charges to count, just like before, and we express that as a distribution of charges, just imagining there's like infinite numbers of little charges that are all sort of packed together. We're going to do something kind of like that with a bunch of charges distributed in a ring, okay? And again, it's going to work the exact same way. We're going to imagine there's a little bit of charge in a little bit of that ring, and then we're going to see what the potential is over at some point from that little bit, and then add up the contribution from all the little pieces of the ring that each contain some charge. The thing is, this time I'm not going to think about like, oh, there's like a vector and some of the components maybe cancel out and some don't. I don't have to think about that. I literally get to just use the integral to just add it up because it's a scalar, which makes life a lot easier. So we're going to express this in an integral form to allow us to do this. So I could write v as k, or 1 over 4 pi epsilon naught, times the integral of dq over r. And we'll call this the integral form of the exact same equation. It's just now we're breaking up the charge into little segments of charge. So if I want to use that equation with this example, this ring of charge, watch how quickly we arrive at an answer. It's kind of ridiculous. So first of all, this r that's there, if I'm trying to find the potential at this point that's like some distance x right away from the middle of the ring, well then over to any point on the ring, the distance r is this hypotenuse. And that value is constant, okay? No matter where I go on this ring, the length of that hypotenuse is exactly the same, and it's the square root of x squared plus r squared, the radius. It's going to be a constant value though. So I can go ahead and pull that out of the integral. So I've got k over r dq. And then we can express r as what they have there, the square root of x squared plus r squared. So I've got k over the square root of x squared plus r squared, integral dq. And we're basically done, believe it or not. If I'm just doing the integral of all the little pieces of charge, what is all the little pieces added up? It's just q. So this is kq over the square root of x squared plus r squared. Wow. That was fast. That happened ridiculously fast. kq over that distance. So what happens if I get very far away? Let me just see what happens. Very far away from this. In other words, if x is much greater than much. I can do this all day. You get the idea. Much greater than the radius. So instead of looking at some distance x, we're just going to let the x be way over here somewhere and try to find out what that would be. Well, I can take a look at this equation and say that now x squared is going to dwarf r squared by comparison. So essentially the r squared isn't even there anymore, and I just have the square root of x squared, which means that my potential becomes kq over what? Just x, right? Where x is the distance away. Well, that looks a whole lot like this. We're just using x instead of r, but both are just a distance. Which means if I get far enough away, this ring of charge looks like a point charge. And that fits, right? If something's a disk and I get far enough away from that, all I see is a point, okay? So this equation seems to fit with what we would expect from a great distance. And we're done with that. That wasn't too bad compared to some of the other calculus examples we've had, I don't think, okay? So let's jump over here, and I've got some other questions to give you. We talked about these equipotential lines and surfaces, and I drew this diagram, but we didn't actually talk about the problem that's sitting on that page. At which point, 1, 2, 3, 4, or 5 is an option, would the potential be equal to 0? Notice they drew a line down through here. This is an equipotential line. An equipotential line is a line on which all the potentials are the same, and all of those are equidistant from both the positive and the negative charge, which means all of them are going to have potential equal to 0. Okay? What about this one? Which 2 points have the same potential? Don't think about this for too long. Which 2 lie on an equal potential line together? Looks a whole lot like C and E are both on this equal potential line that goes around closest. So our answer there is number 4. Okay, equal potential line once again. I already decided to skip the electric dipole stuff. Turns out we don't really need it for this class, so I'm going to jump over that, which brings me to the last 2 slides of this chapter, and then we're going to do some review stuff, all right? So electric field from electric potential. In other words, if you have the electric potential, which remember is a scalar, which remember is easier to calculate, we can go from there and calculate an electric field. If you have the potential, it's possible to go backwards and find the electric field without having to do all of the vector work. So you might remember we had an equation that kind of, let's see, it sort of looked like this. We said it was the change in potential over D. We had an equation that looks like that connected the 2. We used that to say that the electric field is the negative slope of the potential. The electric field is the negative slope of the potential, and we used that idea together with our 3-dimensional diagrams to see how the potential is changing, and it had all of those little pink, purpley sort of lines on there that we said represented the electric field, and it was literally the slope of the potential. Well, I can re-express this equation just a little bit and write it as E sub L, where L is just some arbitrary direction. In other words, it's one of the components of the electric field. It's just instead of saying X, Y, or Z, I'm just saying that way. Or maybe it's this way. I don't know. I'm not picking one of the directions. So I'm speaking really generally here. The component of the electric field in some arbitrary direction L is equal to the derivative of the potential with respect to that particular position. So again, we're dealing with the negative slope or the negative rate of change of potential in that particular direction, that L direction. So let's write down a couple of different things about what this means. First of all, this is mathematically known as the gradient of the potential in the L direction, in case you're familiar with that terminology. And it is the negative rate of change of the potential in the L direction. The negative rate of change of potential, which is defined as the gradient of the potential. So to put this in terminology that maybe you like a little bit better, we could find the X component of the electric field and the Y component and even a Z component if we had 3-dimensional situations. We're finding the components of the electric field vector. We can use this particular equation in all 3 directions. So instead of some arbitrary L direction, we can write this in terms of X, Y, and Z, which we're a little bit more familiar with. Except if it's a function of maybe X, Y, and Z, I have to rewrite that as partial derivatives. So this would be the partial derivative of the potential with respect to X, and the partial derivative of potential with respect to Y, and negative the partial with respect to Z. And you might remember, or may not, that when you're doing a partial derivative, it just means you're going to take the derivative with respect to that one variable and hold the other ones constant. So your equation might have x's and y's and z's in there. Just pretend when we're dealing with x that anything with y and z is just a constant value, okay? And you're not having to worry about that at all. And let me do a quick example of this for you, okay? So let's say that we had something like this. The potential as a function of x, y, and z. Meaning maybe we have an equation that we could plug into the computer and get it to graph one of these pretty three-dimensional things that tells us what the potential is at every point in space. And maybe that function looks something like this. 2x squared plus 8y squared z, and who in the world knows what this looks like, plus 2z squared. Maybe you plug that in and get it to graph that in 3 dimensions for you. If we wanted to find ex, well, then we look at that function and again take the partial derivative of the whole thing with a negative sign with respect to x, making sure that anything that has a y and a z, we just pretend those are constant. So when I take that derivative, that's just a 0. We don't have to worry about it at all. So for this one, the derivative is going to be 4x, and we would throw a negative sign in front of it. So ex is going to be minus 4x. That is the component of the electric field in the x direction. And ey, we could do a similar thing. In this particular case, well, I have an x here. This one's going to be 0. We have a z over here, so this one's going to be 0. And we can pretend that the z in the middle is, again, just a constant. So in this case, we would have minus 16, and we could put the z in front to pretend it's a constant, times y, minus 16y. And the z component of the electric field would be expressed as minus 8y squared. The first term is constant, so it's just 0. This one, we're pretending that the y squared is a constant, so everything is constant out in front of the z, so that's just minus 8y squared. And the last one would be minus 4z. Those would be the equations for the components of the electric field at all the points in x, y, and z space, okay? So you can do a lot of work in 3 dimensions if you know the function, and you can like very, very quickly get to the answers. And of course, if you wanted to say like, oh, well, what is the electric field vector at this point? Like maybe at the ordered pair 1, 1, 1, x equals 1, y equals 1, z equals 1. We'll just plug the numbers in, and it'll tell you what the 3 components of the electric field are at that point. And you could do that for all the points, and all of a sudden you have a nice, pretty graph of everything that's represented once again, okay? Any questions about that one? Before we do the last slide, which I have nothing hardly to say. It's just a different unit that you may sometimes see, and I want to make sure that you're aware of it. And it is the electron volt. 1 eV, the electron volt, is equal to 1.6 times 10 to the minus 19 joules. It turns out that a joule of energy, and we were talking at the start of the chapter about potential energies and dealing with that, a joule is really, really, really big. And we're dealing with things that are charged like electrons and protons. So often, instead of having to deal with 10 to the minus 19 on everything, it's just easier to re-express really small energies in terms of a different unit, like electron volts. It turns out that the electron volt is defined as the energy required to move a charge equal to the elementary charge, and keep in mind that's 1.6 times 10 to the minus 19 coulombs, through a potential difference equal to 1 volt. A, B, so in other words, if I had an electron and it was at one point and I wanted to push that electron over to another point that had a different potential that was 1 volt in difference, 1 electron volt is how much energy would be required to do that amount of work. So often when we're dealing with atomic things, electron volts are used for energies instead of joules, just because it's a little bit easier to work with, and some of your homework problems could have things in electron volts, and just want to make sure you're aware of that, okay?